Okay, hello. Welcome at the second part of our exam 2 review session. How is everybody today? Good, hi. Hi, good afternoon, good afternoon. Yes, thank you, Eva. I'm very well, thank you. Thank you. No, we don't. I mean, we have to be stressed a little bit, because if we are completely relaxed, then we can't really study. Yeah? We have to be, because the little amount of stress will like keep like pressing and keep us like working. Okay, that's, we have to be a little bit stressed, but not like stressed in the bad way. No, just a little bit for us to like keep going. I can just repeat myself. You can focus on the sample test, you can focus on the set of these problems, and this especially the lesson 8 optional 2 quizzes. Yeah? For the sequences and for the series. They are really good selection of questions and really good exam type questions. I mean, that's everything what I just said are good for your exam 2 review. Tiffany, what did you say? Dust and chalk. Okay, I see. Okay, I got it. Now, I mean, it's, yeah. It's okay. Yeah. I think I got it. I think I got your joke. Okay, Afin, what you saying? Yeah, you can definitely rewatch the session and you can hear me again. But yes, I did set sample exams, practice exam, and 2 optional quizzes, which are practice quizzes, but they include quite good questions. Okay, let's work. And of course, this session, that was, I believe, the exercise from yesterday, the last one, sequences, and we kind of like finished. But also, if you're going to rewatch the session from yesterday, the part 1 of the review, we did spend good amount of time on indeterminate forms and computing the limits. Please note that I might just change the function for the sequence and ask the same expression, the same limit, asking for the sequence if it's convergent or divergent. Okay, and sequences and the limits, I mean, let's say sequences. Sequences are when we have the question, we're not applying any tests, we're not thinking about the test, we're just computing a limit of the sequence, limits at infinity. Okay? And if the limit exists as a finite number, the sequence is convergent to that number. If the limit doesn't exist or is as a finite number or doesn't exist at all, is infinity or maybe undefined completely, then we will say the sequence is divergent. Okay, that's it for the sequences. And you can look at those again. We also did this one. Oh, did you compute number 8? I think it's 1. We can do it. We will add a slide. Who compute number 8? You probably forgot. It's okay. We can try to compute a limit, and I can rewrite in terms of x, because applying the L'Hopital rule with taking the derivative, and when we see x, we have at least the feeling that the expression is continuous. When we see n is like discrete mathematics, only defined for the positive integers, and we're not technically like allowed to differentiate discontinuous function. Okay, so this is 1 over big number, small, 1 over big, small, 0 to the power of 0. Let's just see what we can do. I will not suggest to guess the answer. No, let's do it. power form. We will rewrite our form as a e to the power of ln of this quantity to the power of this of 1 over x. Can we see this? Okay, and then maybe one more time, limit and e, and that power, that exponent 1 over x, we may place in front. Okay, and now limit we can apply to the exponent. The final answer will be limit in that exponent e to the power of this, and I can possibly put this a little bit too high. We may notice we can put this logarithmic function on the top of this fraction. Okay, that means the final answer is e to the power of that number. Let's find out what is this limit. Limit as x goes to the infinity, natural logarithmic of 4 over x over x. Okay, first of all, let's check. This is infinity. 4 over big number is small number, and logarithmic function at 0 at small number is going down. We remember I was drawing, and I think I draw, yeah, this is logarithmic function and goes down at 0 from the right hand side, ln of x. Okay, infinity over infinity, doesn't matter if it's negative or positive, it's infinity over infinity, indeterminate ratio form. We are allowed to use the L'Hopital rule. Let's see. Derivative of x is 1. I can start with the denominator. Derivative of ln of 4 over x, it will be 1 over 4 over x times derivative of 4 over x. Derivative of 4 over x, 4, and then 1 over x. Derivative of 1 over x is negative 1 over x squared. Oh, a little bit too. 1 over 4 over x, I can flip as a x over 4, and then negative 4x squared. And 1, we may ignore it. Okay, do you see the answer? We can simplify those, and we can simplify these quantities. Negative 1 over x. And actually, 1 over big number is a small number. Negative in this case doesn't really, it's not affecting because we do not have negative 0. Okay, 0, but what is the final answer? What is the final answer? Please tell me. It is actually 1. The final answer is e to the power of 0. Okay. Yeah, probably 0 to the 0, we may guess that is 1, but it's always worth to check. We don't know. Yes, we definitely don't know. Okay, let's focus on the infinite summation series, yeah, the sigma symbol, and all of the tests. I believe that's the still sequence. Okay, since I have this question, who can answer this question as a warm-up? Determine what the 5 to the power of n minus 1 over 3 to the power of 2n. Which answer you will choose? Let's say this is one of your first questions from chapter 10, one of the. Okay, Afin gave us the answer. Maybe more students. And also, if you're just watching, if you're not attending live, you can also try to answer the question. Okay, couple of seconds. Yeah, we should know this answer right away. How this expression. Okay, Tiffany gave us the answer. Afin gave us the answer. More students, more. Eric gave us the answer. Yeah, maybe a couple of more students. because we're not using any test, we just finding, we can even say this, and this is actually, and definitely denominator grows faster. The answer is 0, converges to 0. Yeah? So we have to be, yes, we have to be careful with this 5/9. No. It's just telling us that this expression 5/9 to the power of n will approach 0. Okay, that's good. Yeah, that's the leading functions. Oh yeah, I know. Why wouldn't be 5/9? But I don't know how to answer this question. 5, because we, of course, we can combine this together, 5/9, and this is actually 1/5. Because the numbers which are less than, if this number, this is like a geometric sequence with common ratio 5/9. Or if we like to look at this as a function, okay, let's say the numbers like less than 1, like 1/2 or 5/9, they all, for the exponential function, they behave like this. But we're just looking at these numbers. I included 0 is fine. Yeah, they definitely approach the numbers if the common ratio is less than 1 and between. Okay, let's say positive for now, because I just draw. I don't want to have positive for now. Okay. You can, if you want more explanation, you can check section 10.1, and there's the video with the geometric sequence. Yeah, I was explaining everything in the small details. What if it's equal to 1? Is it divergent? But what is equal to 1? The common, yes, 1 to the power, 1 to the power of, I mean, no, let me, this will be just different limit. Yes, 1 to the power of n. Yeah, let's say this is a sequence. 1 to the power of n. Okay, who can tell me what is this limit? 1 to the power of 1, 1 to the power of 2, it is 1. That means sequence is convergent. Yeah, convergent to 1. Okay, that means not divergent, it's convergent, but a sequence. Sequence, and we have to be extremely careful. Yes, if this will be a sigma in front, the series, if with this behavior of the sequence 1, then we have to think that we're adding 1 plus 1 plus 1 plus 1. Of course, it will be divergent by the test for divergence. Will partial sums be on the exams? Afin, I don't know exactly what you're asking, but yes. Yes, my answer is yes. I can guess what you think. The answer is yes. Okay, that's working. Now, finally, we can talk about the sigma, summations, infinite series. Okay. One of the easiest questions, to recognize the type, determine whether the series is convergent or divergent. If it is convergent, find its sum. If I will ask for the sum, what do you think? What type of the infinite series we will have in front of us? The geometric one. Because rest of the tests, they're not giving us actual sum. They will tell us if the series is convergent or divergent, but only geometric we have some formulas. Okay, that means let's figure out the common ratio. I mean, no, first of all, do you think this is the geometric series? Do you think it's geometric? 3 to the power of negative 3 and 4 to the power of n plus 1. No. Yes, it is. Yes, thank you. Yes is the correct answer because n, yeah, the quantity n is placed in the exponent only. That's how we can recognize. We can see 3n, n plus 1 only in n. Now we can grab the entire formula that is taken to the power of n, let's combine it, and that will be the common ratio. Okay, who can tell me right away what is the common ratio? I would like my students to, oh, you are faster than me. Yes, that's really good. 4/27. Okay, you can see this, that's good. Okay, and then this common ratio, 4/27, is between -1 and 1. Then the geometric series is convergent. Yeah, we can say the geometric series converges to S. And what is the formula for S, for the sum? Please just tell me, I will put this theoretical part in that corner. The sum is the first term 1 minus common ratio. We have to know this. Yeah. Oh yes, okay, Afin is typing. A means the first term. Okay, we might rearrange a little bit. We don't have to rearrange completely. But what I will do, I will rewrite this like that. 4 to the n, 4 to the 1. And then we have 4 to the n, 27 to the n, and times 4. And now we can definitely see that is 4/27. This is the quantity taken to the power of n, and that's the common ratio. Okay, but you saw it right away. 4/27, yes, that's good. Okay, that means now let's, oh, no, one more thing. What is the first term? Because we will need a. I can put a sub 1, but please remember that 1 just representing the first term, not like, yeah, like the first term. We have to take our expression and substitute that number 1, yeah, in this case. That we will take, maybe even this one is good, yeah, unless we didn't make like any mistake. 4 to the power of 1 times 4, 16. Thank you. But I would like to make one more comment. We did substitute instead of n1, but if this will indicate like that summation starts from n equals to, I don't know, let's say 3, then we will substitute 3. For a sub 1, we will substitute 3. The first term is defined for 3, for instance. So please also be careful, not always 1, but this one is 1. Okay, and then the sum is the first term, 1 minus the common ratio. Who can give us the answer? 16/23. Please. Correct. And that's the summation, 16/23. Yeah, because 27 minus 4, 23, 16/23. Yeah, okay, thank you, Cameron, that's good. Okay, this is the sum. Actually, converges to 16/23. Okay. Important geometric series, definitely. Okay, do I have one more? Oh no, it's okay. I thought that I have one more, but we don't have to practice over and over the same concept. Okay, what about this concept? Who remembers? Also quite quick and nice, easy question if we remember the concept. Okay, if the infinite summation, the summation, the series a sub n equals to pi, then find the limit at infinity of the expression cosine of a sub n plus 4 over a sub n plus 6. What is the answer? Okay, Cameron gave us the answer, and okay, I see, and Sveta gave us the answer. Somebody, one more? Okay. Oh, Ava. Oh, okay, Ava. Oh, I'm sorry because you didn't type 5/6. Yes, you're right. You did put a. Yes. Thank you, Cameron. Yes, of course, this is the correct answer because we remember this information is just telling us that this infinite series is convergent. Okay, doesn't matter if it's pi, 2 pi, 5, 6, 7, it's convergent. And if it is convergent, the behavior at infinity of the terms of the sequence, they have to be 0. Yeah, it has to be 0. If the limit is 0, we still know nothing. But if we know that the infinite series is convergent, the limit of the sequence is always 0. Okay. That means Ava was the first one who got it and gave you some. Oh no, Ava, it's fine. You don't have to put no. It's my because I saw 5/6 and I didn't. No. Any note, any typing, it's good. Okay, so now the limit that we are asked to compute is cosine of 0 and 0. Plus 6. Cosine of 0, of course. Am I adding in my head? And yes, 5/6. It's such a nice and easy question. And please don't miss this question. Okay, please don't miss because it's so easy. Okay. Also nice question. Now I can, if you can answer this question, I will know who is practicing the optional quizzes. Okay, let the sigma a sub n, the infinite series be the sigma a sub n be the infinite series whose sequence of a partial sums is given by this formula. That's in partial sum. We know what is partial sum, the new sequence. And then what is the sum of this infinite series? Yeah, I think everybody is perfectly correct. The summation, it's basically the behavior of the partial sum at infinity. If we have the formula, we're not always lucky to have the formula. And this limit, we recognize the formula 5/n to the power of n. We remember that this limit 1 that's 1. I think we didn't. A and B. Everybody's perfectly correct. E to the power limit of the sequence of a sub n. This is the limit of the partial sum, like keep adding 5 terms, 10 terms, 15 terms. Yeah, that's the sum. Yes, of course, if this exists, if the number will not exist, then we will just put, oh yeah, I guess infinity will be the option. Okay. Now let's look at this. True and false questions. I might ask you again, doing the optional quizzes, you probably saw the format. Okay, a sub n, it's corresponding like a function f of n. where f of x is a positive, continuous, and decreasing function. Yeah, that's the condition for the integral test on the interval from 1 to infinity. And improper integral from 1 to infinity f of x dx equals to 4, then the corresponding series is also 4. Do you think it's a true statement? Everyone, true or false? We have 50-50 chance. I hope we remember it's false. It's false. We can compare. If the improper integral is convergent, then the infinite series is convergent. If the improper integral is divergent, the infinite series is divergent, but they never the same. If you can check, section I think was 10.2 or 10.3, I was drawing like this rectangles, which represents the area of the rectangle, represents the terms of the series, and always the rectangles were a little bit below or a little bit above the curve, and the area under the curve is the integral. That means they were always not the same. We can compare, we can make this comparison, but they never the same. Okay, that means the integral, let me just, this is the true statement, not the same. Comparable, we can compare. Okay, but they never they're never the same. Okay, now another question. If the limit of the sequence at infinity is 0, then the infinite series, the corresponding formula, is convergent. Cameron, that's a really good comment, of course, because most of our formulas, they go, the sequence goes to 0. Of course, it's false. And the beautiful, like, what is the example for this to kind of prove it? Yes, we know nothing. Yeah. Harmonic, 1 over n. That's the harmonic series. Divergent. And what about the limit? At infinity, limit is 0. Limit 0, but we do have divergence. Yes, 1 over n. Thank you. Good. You ready? Looks like you're ready. Okay. What else I have? Now let's work on those. That's the most common question. Determine whether the series is convergent or divergent, and what test we use. Okay. This one, really easy to answer, almost like less than a second. Okay, Afin, I don't know, you contradict. Yes, of course, is diverges by nth term divergence test. I think I like to say test for divergence. Okay, the nth term divergence test. Okay. Yes, test for divergence. That's what I just like. I like to say, but we can say the nth. Somebody, I think, the nth term test, the nth term divergence test. Yes, Afin, I saw that you mixed. The limit is not 0, right? If the limit is different than 0, then we have no chance for convergence, because we have to think with respect to the addition, to the sigma. Like, we will have the first term, we will add the second term, and then we will keep adding the terms which are almost that. Yeah? Of course, this will be huge. We can think this way, right? We can try to because that sequence is convergent to 4 over 3, but no, the summation of 4 over 3, of course, yeah. No finite limit. Really good, really good. Let me, actually I can say divergent because infinity is, yeah, but it's, okay, good. What about this one? Converges or diverges? -1 to the n over ln of n. Yeah, now I have like a mixture of you may notice I'm not asking for the absolute, then we will get to this. Yeah, we have to take the formula like it is, we're not changing anything. Afin is suggesting the AST test because we can see alternating part, -1 to the n, and yes, we can try to use AST. Let's see, AST is a good, but let's see if this works. Integral test, I don't know if the integral test will work because for the integral test, let me come back. Do we see the condition? Where we are. Function must be positive, continuous, and decreasing. Yes, for integral test, positive. Okay, that's we not really, if we see the alternating formula, we will not really, the integral test will not work unless we take absolute value and test absolute convergence. Yeah? Okay, but now let's see, AST, we have to pull out the positive part, I mean the main values, ignoring for second -1 to the n, b sub n. And yes, I can see Cameron is listing. Okay, b sub n is positive. Limit, is this limit 0 at infinity? And b sub n must be decreasing. Decreasing limit 0. That means this is correct, and I think it's decreasing because only I can write ln of n, and the next term will be ln of n plus 1. If the denominator is greater, the whole fraction is smaller. That means the next term is smaller and smaller and smaller. Okay. And of course, logarithmic function is increasing, then this is greater. Okay, excellent. We're satisfying everything. We may put the final note. Actually, let's say 3. Because the logarithmic, we know. It's convergent. Okay, by AST. AST and converges. Celiang, do you understand that we are not allowed to use the integral test? Yes, okay, good. Just to, and for the AST, we really want all of these 3 conditions to be satisfied, because if one of them is not, we're not satisfying one of the conditions, then we're not even allowed to use that test. Yeah, we have to find different tests. B sub n smaller, denominator greater, fraction on left. Yes, if the denominator is greater, the whole fraction is smaller. Yeah, that's what we can see, and that's the next term. B sub n plus 1 is this, and then again, B sub n plus 2 will be even smaller, This is just down, double checking, decreasing. Of course, derivative is a good tool to check the decreasing, but we don't have to for this nice and easy function. Okay, now let's answer this question. The same formula, okay, the same formula, however, absolute convergence. Do you think this series is absolutely convergent or conditionally convergent? It's definitely not divergent, because we just prove it. I can switch the slide for a second. We just prove it that this original formula is convergent. I mean, now is the only case. That means definitely not, that's not a case. But what do you think? If we will take absolute value, are we getting convergence? Let's test. Absolute value will, too many limits. Absolute value will give us, let me start from 3. We know why. Natural log of n will stay natural log of n, negative 1 to the n will become positive 1 always. Okay, 1 over ln of n. Eva is saying is absolutely convergent. Okay, we have to, how we can prove this new, because that's the new formula for us, the absolute value. If this formula is convergent, then yes, the series is absolutely convergent. If this formula is not convergent, the series is not absolutely convergent. However, it will be conditionally convergent because the original formula tested on the previous slide was convergent. Okay, we may try to compare. What do you think? Maybe 1 over n. I'm trying to compare. Let me write the fractions. Natural log of n. Comparison test is good when the terms are positive, and we have positive terms. Divergent, larger, yeah, okay, that's me. Let's see if this works. Natural log, if I will draw natural log and n, this is n, this is ln of n. ln of n is greater. That's mean, yeah, Cameron, that's really good comments. Correct, actually, solution. N is bigger. If the denominator is bigger, the whole fraction is smaller. Perfect. The same, yeah, we can keep the same relation for the same number of terms when we adding them. And yes, this is divergent series, of course, harmonic, and everything what is bigger is also divergent. Yes, we can say that by direct comparison test, this is divergent. Okay, divergent, and we were comparing with 1 over n, divergent. Okay, that means that was absolute value. Absolute convergence is not a case. Then everybody is okay that is conditionally convergent? Because normally what we will do, we will take this, if we getting like divergence for absolute convergence, then that's not the case. We supposed to look at the original formula. Yes, that means this is the first step. I took absolute value, and it's not, yeah, it's not absolutely convergent. Then the second step is look at the original formula and test it original. No absolute value, nothing. We can use any of our tests to find absolute, yes, because we're taking absolute value, and then you can use almost any test because the terms are positive. If, of course, if the formula satisfies the condition for each test. Yes, that's correct, Eva. Okay, that means it's not absolutely convergent. Now we're looking at the original formula, and we know, we just did on the previous slide, that this is convergent by the original formula is convergent, but not absolutely convergent, conditional convergence. That's the example of conditional convergence. Okay, that's, we can see for the conditional convergence, we have to get divergence and convergence. Yeah? Divergent for absolute value, convergent for the original formula. Limit comparison test. Yes, I think we can use limit comparison also. Yeah, if you can find something good to compare with. I don't know if this will work. If we will compare the limit comparison, I don't know, because because we have to divide a, yeah, that's the limit. A, this is ln of n, and this is n. And n grows faster, we will get infinity. And infinity is telling us that n. Now, I think direct comparison, because as soon as we're getting infinity, I will be really careful to make some conclusion. For the limit comparison, we're really looking for the finite number. Because if that limit is a finite, positive, like non-zero finite number, then we can always conclude that our original formula behaves exactly the same like the known one. But when we're getting zero or infinity, then it's a little bit, I will not recommend, okay? Because then the conclusions are a little bit different. We have to look at different conditions, and we already have long list of other like tests. Yeah, direct comparison. If the direct works, then we don't have to use the limit. Okay, let's look at the next. Okay. -1 to the n, 1 over 1 plus natural log of n. Absolutely convergent, conditionally convergent, or divergent. If you have to guess what you will do, please tell me. If I will force you to guess, yes, you will definitely use AST, yeah? But AST will not answer absolute convergence. But yes, AST, and everybody is okay that by AST, this formula is convergent. Yeah, using AST, B sub n, yeah, it's positive, limit is 0, and it's decreasing. That means it's the same situation. It's convergent by limit of B sub n is 0 at infinity, and B sub n is definitely decreasing. Check, check, decreasing, check. The infinite series is definitely, oh, let's put 3. Convergent by AST. By AST, let me make a little bit. Okay, we good with this. Okay, but now that means it is convergent by AST, convergent as original formula. This is not a case again. Yeah? Okay, let's test absolute value. -1 to the n, 1 plus ln of n. Do you think this formula is similar that the formula that we just did? 1 plus ln of n will stay, and 1, -1 to the n will become simply 1. Okay. And what we think? Because the previous formula was 1 over ln of n and was divergent, definitely divergent. And I will like, if I will look at this, I will just think, oh, just adding 1 is like a fine. Probably it's not changing much. It's still divergent. And that's mean I will say the absolute is convergent, but since the original formula is convergent, then it's conditionally convergent. Okay. Or can you hear me? Afin is saying, I hope my internet. Oh, okay. Of course, not but now. Okay, okay. Please tell me. No, I was just saying that this formula, why it is okay. I will. One thing, like looking at this formula, it's what I will think, I will like, because we just did an example almost identical. Yeah. And I will think that just adding a finite number will not really change our convergence. Yeah. 1 over ln, that means the situation will be the same. It has to be conditionally convergent. Okay, that I will just kind of like not guess, it's an educated guess, because we did, let's look at this, we did the entire work for the just ln of n in the denominator. Now we have ln of n plus 1. That's what I was saying. But let's actually do everything. We can see it's convergent by AST. Then the divergence is not a case anymore, but absolute value, we have to test it. We're guessing that absolute value, yeah, is not convergent. But let's prove it. We have the formula 1 plus ln of n. How would you, what test you will use? What do you think? What test you will use? We will get direct comparison. Yeah, we can still try 1 plus n, right? 1 plus n. And n is greater. If the denominator is greater, the whole fraction is smaller. But yes, I was thinking, but then the limit will be are we forced to use the limit now? Because how do we know? I can still try to compare with 1 over n. Oh, okay, I know. It's, but the inequality doesn't work really good. Yes, and I think now the limit comparison. Okay, let me remove this one. We can compare this way, definitely. I'm just thinking. But when we put Ava is suggest, no, we can definitely do it, and we can see is divergent. But when we will put Ava, you suggesting just ln of n? But if the denominator is bigger, the whole fraction is smaller. And I don't think we like this inequality, this direction. Yeah, we will not like it. No, I think that was good, but the only 1 plus n, I only replace n is greater. The denominator is greater, the whole fraction is smaller. But now we have to prove it that this formula, it's divergent. Yeah. Let me put divergent. We will prove it in a minute. We will use the limit comparison. This is divergent, then everything what is bigger is also divergent. Okay, let's just like, because then we kind of missing. Okay, that means this is divergent, okay, by direct comparison test, and we comparing with this formula. However, we still not sure if this is divergent, because yes, like how do we know that this is divergent? Well, let's see if let me just add quickly a slide. Because that's what you can do. You can just take this formula on its own. And what we can compare with. Let me just put the sigmas right away. Okay, what is the good formula to compare with? 1 over 1 plus n. Oh, nothing complicated. It has to be 1 over n, because this is almost like 1 over n. Can you hear me, or you can't hear me? Maybe. I hope you can hear me. Please tell me that you can hearing me and seeing me. Okay, okay. Because different thing is that if you're not responding, all different thing is when you're not hearing. Yeah, that means we can see this one. We have to use. It's no other like. I know. No. If it's the silent because you're thinking about the answers, that's good. That's good. Yeah. Yeah. I don't know the answer, of course. But we can see if you see formula like this one, what we can compare with. It's just that finite one is not. It has to be 1 over n. But let's actually check which fraction is bigger or smaller. You can tell me this. Which way shall I put the inequality? The left-hand side? The first one is the left is smaller. The left is smaller. Really good. And we can see this one is definitely divergent. Something what is smaller, we don't know. Bigger than divergent, it is divergent. That means we can say that direct comparison test is not working. We will use limit. Limit. We have to check. Yeah? We will check limit comparison test. Hopefully it will work. A sub n over B sub n. A sub n is the original formula. B sub n is the new formula. And when I flip the fractions, what is this limit? It's not 0, not infinity. We good to use this limit. N over n, the limit is 1. Thank you. Positive number. Then, if the limit is a finite positive number, we can conclude that both of them behaves the same. Yeah? And then now I can say that this formula, okay, I can switch. This infinite series is divergent because this is divergent. Because the B sub n was divergent. That means yes, by limit comparison, and we use limit comparison for this one, just for this one. Okay, that means if we figure out that this one is divergent, let me come back. Then yes, this is divergent. We prove it on the next slide. And now by comparison, the very, very original formula is divergent. Okay, that was absolute value. It's not absolutely convergent, and it is conditionally. And you may notice again, conditional convergence always involve both convergent for the original one and divergent for absolute value. Yeah, that's the conditional. Conditional convergence is always like more time consuming. Okay, it will be good. Let's see. Okay, this one. Absolutely convergent, conditionally convergent, or divergent. But looking at the formula, what test you will use? More AST. Okay, but let's think, because the formula is a little bit crazy. What formula we can use? Oh, no, not formula. Oh, Kasia, what test? I was thinking about the test. We can use the root test. Ratio test will also work, but I think root test, who said root? Eric said root, because we can see that almost the entire formula is taken to the power of n. Yeah? 5 is the constant. We don't have to put. That's what we can do. Let's try the root test. Root test is telling us the n root of absolute value of these terms. The nth root absolute value, of course, will remove this -1 to the n. It's okay, we don't have it anymore. And then we will have, I can put 5, and then I can put n squared to the power of n. Actually, I just want because let's just rewrite a little bit. 3n plus 1 squared, and we have n squared, and everything is to the power of n. Do you see what I did? Now I think will be a little bit nicer form. That's the green n. I left n squared, I left 3n plus 1 squared, and 5, we can see 5 is not taken to the power of n, but 5 is constant. Actually, I don't want green. 5 is constant. I can put the constant outside. It will be just 5 times the sum, if the sum exists, but we don't know yet. Okay, now let's do that form. N squared, 3n plus 1 squared, and everything to the power of n. Yeah, that's the green n. Because having that form, we can nicely see the nth root and the n power can cancel out. And now, what is the limit of this? Please tell me the limit is, if we will keep that 5, but let's don't keep this 5. Let's don't keep this 5. Yeah, I will just focus on that. Multiplying 5 times something finite, it will be still convergent. 5 is, that constant 5 is not affecting. Okay, 1/3. Oh, okay, Eric. Can everybody see what Eric typed? Because when we do the expanded form, this one is done. This one will become 9n squared. 1/9, the number is less than 1. Yes, the original series is absolutely convergent by root test. Because we remember the number must be less than 1. If it's less than 1, it's always positive because absolute value is involved. If it's less than 1, we have absolute convergence. If it's greater than 1, if that limit is greater than 1, is divergent. Yeah? And that's it. If the limit is equal to 1, then it's inconclusive. We can't use it. Why are we not taking? I mean, I can keep that 5, but just to make everything simple. Sveta, do you see this? Because 5 looks like just a constant. Yeah, we're not adding anything, it's just 5, we're multiplying by 5. We can throw the constant because 5 is not taken to the power of n. If 5 will be taken to the power of n, if this will be n, I will keep inside because that green n will affect that. But the problem was 5 is not taken to the power of n. It's just constant. Then it's not part of my n's and all of this roots and simplification. Yeah, I think was much easier. Okay, 1/9, and yeah, this is absolutely convergent. And times 5, we will have a finite sum. Okay, but definitely root test. You figure out the test correctly. That was my point. Okay, another one. Cosine of n pi over n. Do we remember cosine of n pi? How cosine of n pi behaves? Cosine of 1 pi. Yes. Oh, thank you, Afin. That's really good. 2 pi. Yeah, 3 pi. We remember this is -1, +1, -1, +1. And behaves like net n. Yeah, that's the point on this question. Instead of cosine of n pi, you can rewrite as a -1 to the n, and this one is alternating harmonic, and it's conditionally convergent. You can do the test. It is convergent by AST, and absolute value is not convergent. Okay, you can do this, no problem. Okay, formula like this. negative 3 to the power of n, 2n plus 1, and factorial. What test will be good? Please tell me. Of course, the ratio test. As soon as we see factorials, I will use the ratio test. Let's do it. Okay, ratio test. We need a ratio, I mean the limit, a sub n plus 1 over a sub n absolute value. Yeah, absolute value will definitely, because this we can rewrite as a negative 1 to the n and 3 to the n. Okay, that means absolute value will take away that negative 1 to the n. Okay, but now, first of all, we need a sub n plus 1, 3 to the power of n plus 1, 2 times n plus 1 factorial, and dividing by a sub n. I will multiply by the reciprocal, actually. 3 to the n, 2n plus 1 factorial. And okay, I can put absolute value, but we don't need, since each term is positive. Let's do the simplification. 3 to the power of n, 3 to the power of 1. 2n plus 1 factorial, 3 to the power of n. This one we have to distribute. 2 times n is 2n, 2 times 1 is 2 plus 1, 3. Okay, we simplifying this, but we also have these factorials we have to simplify. We have 2n plus 1 and 2n plus 3. 2n plus 3 is number 2 more than 2n plus 1. Yeah, like for instance, 5 factorials over 7 factorial. Yeah, because 7 is 2 more than 5. Then I will keep 5, I will keep the lower number, and 7 I can rewrite as a 5 factorial times 6 times 7. Do we agree with this? And then we can cancel out. That means what I did with that 7, I subtracted 2, I got 5, and then 5 factorial, and then times 6 times 7. That's what I will do with this one. I will say 2n plus 1 factorial, n times 2n plus 2, 2n plus 3. Yeah? We can picture that that number, 2n plus 3, is like 7. And we can see, I did subtract 5 because I would like to match to the number on the top, 2n plus 1 factorial, and then 2n plus 2, 2n plus 3. I hope that makes sense. And now we can cancel out these because that's the identical terms. Okay, and what's left? Let me write here. We will have 3 on the top, and we will have 2n plus 2, 2n plus 3. Okay, what is this limit? 3 over 2n plus 2. Hang on. Afin said 3 over 1. No, that's not the right number. And Cameron is saying the achieve skips lots of steps. You referring to the factorials? Oh, Ava is saying something. Because the achieve homework. Oh, okay. I think I'm losing. I mean, I'm not reading all of the chats. I see the chat, but okay, camera. Okay, who gave us the correct answer for the limit? 3 over n squared. Of course, the limit is 0 because denominator, thank you. And 0 is a good number, is less than 1. 0 is less than 1. Then we can say that this infinite series is absolutely convergent by ratio test. because ratio test and root test is testing absolute convergence or divergence only. If it doesn't work, then we're not using. But if it works, we have the answer right away. Okay. What you can do on Canvas, I believe the very bottom, like you can find the module on Canvas, you can find the module like with my practice videos. And one of the video for section 10.1, like 10.1, like this sequences with factorials. I do a lot, yeah, I did a lot of this simplification. Okay, that means if you can practice factorials, you can check, it's like a sequence because, yeah, a sub n plus 1 is the sequence. Yeah, that means I do a lot of these simplifications. Okay, let me check what else I have. This one, let me check this one. Oh, I know what we have to do. Okay, that's what we can do. Let's 10 minutes, okay? And I will let you go. You can try to do this one. I believe this one will be absolutely convergent. I believe this one will be conditionally convergent. Oh, no, wrong, Kasia, wrong. What is this one? What is this one? Can you tell me right away? N over ln of n. Divergent, because the limit is not 0. It's divergent by the nth divergence test or test for divergence. Okay. This one, I believe you will get this. Just really quickly, one question about the estimate, like to estimating the sum. Okay. Let's just unless we will skip this, but this is important. I don't know if I like to skipping this. No, let's do it, and you will like it. Okay, we will do almost the same question. Okay, for the alternating series, we remember we had this alternating series estimation sum. What this means that we can say that partial sum S sub n, like a sum of the finite number of terms, we can say it's almost the same like the entire sum. And I have these nice lines. That long line represents S. This line represents the partial sum S sub n. And we can say they are almost the same. However, when I take this long line, which represents the entire sum, and subtract the finite number, I have this small difference, this remainder or the error in the estimation, like we will call this. And what this theorem is telling us, without having the entire sum, obviously, we can estimate that difference. We can estimate that error, that remainder. Let's see what we can do really quickly. Yeah. When we take the entire sum minus the partial sum, that's the entire sum, adding all of these terms, adding, subtracting. This is the partial sum. We stopped at b sub n. When I subtract them, positive, negative, then we will end up with that term because everything else will be cancelled out. Okay. And you may notice this will be even smaller because we're subtracting another terms. That means we can say that remainder is even smaller than this next term. And that's it. Yeah? That difference, the entire partial sum, always less than the next term that we didn't use, neglected term, the term that we didn't use because S sub n, the partial sum, ends at b sub n. B sub n plus 1 is my next term. That means the size of the error is always smaller than the next term. Of course, the absolute value of the term. We're not looking at other like signs. Okay, and this is the alternating series estimation theorem. We're talking about the convergent, then we remember these conditions, and then we can use this inequality. That means this is just this theorem. The difference is always less than b sub n plus 1, the next. Yeah? I mean, for instance, if I will say that our sum is almost the same, like adding 7 terms. Yeah? S sub 7 is almost the same like S. But what will be the error? What will be the size of this error, of this difference? This will be less or equal to, can you tell me, B, like what, we don't have the formula, but B sub, can you tell me, 8, yeah, the next term, because I use 7 terms. But the size of this difference will be less than, hopefully small number, less than B sub 8. Yeah. And for instance, if I will do the like 70, let's say 70, what will be the difference? Smaller than B sub next term, 71. Okay. Let's just do one question and we will be done. Let's pick the, is that easy question? I have 2. Okay, let's do this one. Let's do this one. Find the minimum number of terms. We're looking for n of the alternating series -1 to the n over n squared, of course, is convergent by AST. The minimum number of terms of alternating series we need to add to find the sum of the series with the error less than 0.05. That means that error means that the difference, the difference between the partial sum and the actual sum must be less than b sub n plus 1. And we know that this must be less than 0.05. I can like include my theorem, our tool. And we're looking for that number of n. But please notice, we're looking for the minimum number of terms. But what is also important, we're looking for n, not for n plus 1. Not for n plus 1. Okay, that means since we don't have and we will not compute, we can focus on this one. Okay, first of all, please tell me what is b sub n? What is b sub n? What is the formula for b sub n? Oh, look, that's the, I know that is quite, thank you. B sub n is 1 over n squared. 1 over n squared. What will be the formula for b sub n plus 1? B sub n plus 1? What shall I put inside? Instead of n, n plus 1. Okay, now I can do n plus 1 must be less than 5 over 100. And let's just try to solve it. Maybe 1 over 20. Okay. We're just trying to, then I can say, since I'm flipping a fractions, I can flip the inequality. And what we can do? Shall we take everything? It's positive. That's mean we're fine with this. Do you think we can take a square root? Okay, and then n, it's square root of 20 minus 1. Okay, I know doesn't look like, but we have to figure out because this is irrational. But under what circumstances do we flip the inequality? I know this is greater. No, because we just want to solve it. Yes, we just want to solve it for n. We're looking for the n. What is the n number? Because that's the n values. and we're looking what number of n satisfied this. Yeah, that's when I'm just solving. When we have the, I mean, looking at this, yeah, this inequality is equivalent to this one. Because if the denominators, yes, we can see if the denominator is this, yeah, we just flip. I don't want to make a complication because actually you're right. It's probably from I can't even say elementary school, but no, it could be when we have this. Okay, x. Let's say this. Yeah? 1 over x must be greater than 1 over 5. Then x must be less than 5 because we want the whole fraction to be bigger. Then the denominator must be smaller. Cameron? Yeah, when we flip the fraction, we flip the inequalities. If everything is positive, of course, we're talking about the positive numbers. Yeah, like we can see this fraction is bigger, then the denominator must be smaller than the other side. Yeah, like we're doing for the comparison. I hope, Cameron, if you can confirm that you're okay with this, we can try to figure out. Okay, I don't see anything on the chat box. Oh, okay. No. Maybe you missed, but no. It's if you will think a little bit longer after the session, you will say, oh my gosh, it's so easy. Okay, no, you will just, yeah, when we have fractions and then when we flip the fraction, we will flip the inequalities. You can try with the numbers, yeah, 1/2 is greater than 1/5. Do you think 2 is greater than 5? We have to flip it. Definitely, yes. This is just, yeah, as basic as this inequalities. Okay. Yeah, let's figure out what is the number. I think somebody, what is square root of 20? Square root of, because we have to take the integer. Square root of 20, it will be, we know 2 square root of 5, but I don't. Okay, square root of 20 is between what integers? Between 4, because we also have different way of solving this, and I can show you, but we need the integer. Okay, we need the integer, the next integer. This is definitely more than 4, between 4 and 5, right? 4 and 5. And that's mean this number is between 4 and 5. I don't know if I like this way, the solution, because it's not giving me. Hang on, let's. Do you know what? Let's change this one for 1. Because the concept is the same. I just don't want to give you. And then we will, yeah. Let's say for 1, then it's much easier. Okay, let's do this way. And okay, that means now we have, what is the number? 10. Let's just solve. Okay, let's maybe ignore this. We will solve it. I can show you how to solve it different way. That means now it's 10 minus 1, it is 9. As we can see, 9 is the minimum number of terms, because the solution this way, let me change for 1. The solution this way is showing us all of the numbers, and could be greater, because if we increase number of terms, of course, the sum, partial sum, becomes closer to the actual sum, and the error is even smaller. But what is the minimum number of terms? The minimum number of terms is 9. 9. Oh, no, it will be 9. Yeah, in this case, because we can see it's greater than or equal to 9. And we did solve for n. Oh no, but we solve it. That's what I want to, yeah. We did solve it for n. We didn't solve for n plus 1, for n. That means 9 will be the answer. You can pick 9 from the list that will be like provided. Okay, I can, let's say, oh, actually, even this one, we don't have a 9, then we will pick 10. Because that's also could be the case. Yeah? If we don't have that number, or I don't want to confuse you, which I like sometimes, let's say 9, let's say 8, and we will pick 9. Okay, that's the easiest way. But if you have to go, you may go. But let me show you. I will just. Okay, that's we did change the numbers for the calculation. Okay, and we did get, but because I would like to clear the n plus 1 situation. Okay. But this is definitely one of the way, but just in case, yeah, I still want to repeat this. If 9 is not on the list to choose from, you may get another number greater, because all of the numbers starting from 9, we can see all of the numbers greater than or equal to 9 will give us the sum which satisfy this. Yeah, with the error will be smaller. 10 and any number after 9, 10, 11. That means if 9 is not on the list, you will pick 10. Okay, let's look at this one more time, because you might also like this way. The next term, and this has to be smaller than, let's keep it like it is. Okay. If n is greater than 9, so we can't choose 9 anymore. No, we can choose it. We can choose 9. We did get the answer. N is greater than or equal to 9. We did everything like explicitly.
No, what I'm talking about is, what if n is just greater than 9 instead of greater equal to 9?
It is greater than 9, then we have to choose 10. Okay. Because we're operating with the positive integer, natural numbers. Yes.
Okay, thank you.
Okay. You're talking about the yes, good question. Okay, but let's do this one, because what we're looking for the term. Okay, I can copy this one more time, which is b sub n plus 1 is smaller than 1 over 20. Okay, I have to figure out which term is smaller than 1 over 20. And instead of creating this equation that we just did, we can go kind of like step by step. Let's look at this. That's b sub n. B sub 1 is 1. Yeah, definitely greater than this. We're looking for the term that is smaller. Okay, b sub 2 will be 1 over 4, greater. B sub 3 is 9. B sub 4 will be 16, yeah, because we're squaring. What about b sub 5? B sub 5 is 5 to the power of 2. Which fraction is bigger? Now, our b sub 5 term is actually, this is the first term, okay, that's the first term that is smaller, okay? That means this is the first term, the smallest term that satisfies the inequality. Yeah, now I changed the question, because we remember the other question was good. Yes, and now is the moment that when we see b sub 5, yeah, you can see b sub 5, it's smaller than this. Yeah, that's what you like to make. That means 5, represents that quantity. 5 is n plus 1. Then what is n? Of course, it's 4. Yeah, if 5 is n plus 1, because now we're operating, that's what here I would like to make sure. Then you can say that, yes, all of the numbers less than, greater than 4, because n is 4. 4 plus 1 is giving me 5, n plus 1, 4 plus 1. Yeah, that will be wrong. That 5 represents n plus 1. 4, n is 4. I wanted to line up. Yeah, so n number, and if I will keep working b sub 6, b sub 7, it will be still smaller. But because we can imagine that we're adding more terms, then we're making sum bigger and closer to the actual sum. But n sub 4, 4 terms. Yeah, I can even write this property. 4 terms will give us the sum, the difference actually, less than b sub 5, but 4 is the answer. That means this is also a good solution, and that's the original question. I didn't change the numbers. Okay, but we can still do this. This one was, if the number is 0.01, then it works better for the corresponding formula. But this is also, we can go term by term. For bigger value of n, it is better to use the other methods. The other method was way too confusing. Okay, that's Miura. It's not, it's just more explicit. Let me think. For bigger number, yeah, I would say for the huge numbers is definitely, because I don't want to list b sub 50, b sub 51, b sub 50. Yes, 99. Correct. I will use the explicit way. I will use this way. Do we have to use the other method? No, Afi, you don't have to do anything. I'm just always providing all of the options. Actually, I know that the session is really long, but do you think, shall we solve this one? Because this one has a big numbers. It's the same thing. Okay, shall we try? We can try both ways. I will not change the numbers. If you like, if you have time, you can stay with me, but if not, you can watch this later. But since we're talking about this, let's finish. What we know, it's the same idea. We have the alternating series, and we have to figure out what is the number of terms. What is the number of terms that the difference is less or equal to that number. That means s minus s sub n, the error, must be less than b sub n plus 1 and less than or equal to 10 to the power of 4. B sub n plus 1 is 16 over n plus 1 to the power of 4. And I took from the formula. Okay, now we're flipping the numbers. N plus 1 to the power of 4 and 10 to the power of 4. I can take the 4th root of both sides. This will be n plus 1. 4th root of 16 is 2, and this will be 10. That's nice, right? 20, 19. All of the numbers greater than or equal to 19. What option you will choose? What option you use if 19 is not on the list? I know that you, thank you. The answer